And here we go. So 39a, the derivative of exponential functions. So first off is going to be a little bit of a review. In fact, it's going to be quite a lot of review. Lots of things to note, and we're going to be utilizing these facts today and the rest of these weeks. So there is a difference between y equals x squared and y equals 2 to the x. All right. This first one is called a quadratic equation or a quadratic function. And if you were to graph it, it looks like a parabola. The second one is an exponential. You might say, well, there's an exponent there in the 2, right? And the answer is, yeah, but it's a constant. When you've got y equals 2 to the x, the constant is the base, and the independent variable, the x, is in the exponent location. So that's why we call this an exponential function. And it can look a lot of different ways. This one in particular looks like this. All right. Let's talk about logarithms. Before I talk about logarithms, the way this is set up, I throw in a number here, like I throw in 5, and you get 2 to the 5th, which is 32, and that would end up equaling the y value. You can also kind of go around the other way, where I say, here's some value, like here's 32. What is the exponent of 2 that will get you to that number? Okay? So in other words, mathematicians, they're like, yeah, this is great. If x equals 5, then I have y equals 2 to the 5th. If x equals, 7, then this is y equals 2 to the 7th, so 2 times 2 times 2 times 2, and so on and so forth. But what if I know that over here I've got 256. I want to figure out that's equal to 2 to the whatever. Like, what's the exponent? Okay? But they didn't really like writing this. By the way, I think the answer is like, oh gosh, why can't I remember? It's power 2. Anyway, it's like 10 or something like that for that one. Anyway, or, 512. 1024 is equal to what power? When you're asking, what's the exponent right there? They got tired of writing it like that, or actually they never really did write it like that in the first place. They came up with an alternate way of writing this concept, this question. They would say log base 2, so they'd put the base right there, and then of 256 equals what? So they would kind of get all of the numbers and stuff that they could over here on the left-hand side. Or here they would say log base 2 of 1024 equals what? And so the log is short for logarithm, and what it basically means is here's a base, here's the answer, what's the exponent? Okay? One of the common things that students make the mistake of thinking is that they say, 2 to the 7th, that would be like log of 2 and a 7 right there, because they have the same relative position, where the 2 is kind of down to the left and the x is kind of up like a superscript. And they kind of do that here, but that's not the case at all. So let's go ahead and write this a little bit more algebraically. So if y equals b to the x, this is exponential form. Logarithmic form, y'all want to give it a try? Log base, no, not base x, base b. The base is what we would always call the base. Log base b of y equals x. I am periodically throughout the rest of this lesson and the rest of this week, I'm going to be saying, okay, let's turn this from exponential form into logarithmic form, or let's go from logarithmic form into exponential form. So just, I don't know if you want to put a star next to this, but this is super helpful. Okay. That works for any base, any number that you could throw there. You could say, log base 10 is a very common logarithm. In fact, on the calculator, there's a log button, and if you hit it, it'll say log. And what they mean by that is log base 10. Okay. So that's sort of like the generic one. But you could have log base 10. You could have log base 2, which is very common in computer science and programming situations. You could have something weird like log base pi, because isn't pi a number? Yeah, pi is a number. It's a very special number that it relates to circles, which is the ratio of the circumference to the diameter. And because of that ratio, and because it's super important, we designate it with a special letter, with a Greek letter pi. There's another special letter besides pi. Do y'all remember what it is? It's E. It's Euler's number here. So log base E of y equals x. That is sometimes it's called the natural number. Sometimes it's called Euler's number. You might be like, Euler? How do you get Euler from E? Well, the guy's name is actually E-U-L-E-R, but it's pronounced Euler. I mean, like crazy smart. We'll find out. I think maybe next week we'll read a little bit of a biography from him. Unbelievably smart, intelligent. But nobody knows about him, but that's okay. All right, let's give it a shot. Can you convert this logarithmic form into the exponential form? I'll get you started. Y equals, e to the x. Okay, see, so we're doing pretty good. The log base e of y, we use this so often that we have a nickname also for this particular logarithm. And since e is sometimes called the natural number, then we call this the natural log. And we represented it with an L and then n. So we'd say ln y equals x. And what we say out loud is natural log. Does anybody remember? Now, I would not expect you to know this. The approximate value of e, like pi is approximately 3.14. Mm-hmm. 2.72 or 2.718. If you want to go a couple extra digits. By the way, short little fun fact here. E, pi, 0, 1, and I are like, that's it. Like, that's like, you want to talk about like the greats of mathematics and numbers? There they are right there. Pi, e, 0, 1, and I. I remember what that is, square root of negative 1. And it was Euler who actually came up with one of the ways of relating all of those together. You're like, wow, so cool. All right. Let's talk about exponential graphs. since that will be helpful for us. We're going to draw 4 graphs. We're going to draw y equals b to the x. That looks something like this. This is a positive exponential growth. Oh, I guess I don't have all the other stuff. Okay, that's fine. Anyway, I thought I was going to draw the positive growth, negative growth, and decay, and negative decay. I'm actually not going to do that. I'm going to graph the logarithm one over here. So y equals log base 10 of x. And that is going to look kind of like this. So it's going to get looks like it's going to get flatter and flatter, but it's not asymptotic. It just grows really, really, really slowly. Okay? So this is logarithmic growth, but this is, very slow growth in this region onward. This growth is crazy fast. Some people said that humanity will ultimately meet its end because we do not understand exponential graphs, okay, or the exponential relationship. And you can kind of see a little bit of that with the coronavirus pandemic, all right? Because the way that exponential growth works is that if this at 0, we happen to be at 2, and then at 1, we're at 4. It's going to have to be like up here. At 1, we're at 4. Then at 2, you're at 8. At 3, you're at 16. At 4, you're at 32. Okay? It's kind of like if one person gets infected, okay, and then in the course of their brief time when they're contagious, they infect 2 people, okay? And they don't realize it. And then how many, on average, people would they infect? We'll say another 2, right? And then so now there's 4 people. Then those 4 people then go infect 2 more. So now you're at 8. Okay, see what I'm saying? So in about 10 turns, you can get to over 1,000 people. So just 10 of those 1,000 people can catch it. I do want to show you how unbelievably crazy fast exponential growth is compared to, say, just like a quadratic, okay? And I also want to show you how ridiculously slow logarithmic graphs are. Of course, I had to get rid of Desmos. Okay, so here's just a regular y equals x squared. And we'll say something like 0, 5, 20, 100, and 500. All right, so it goes up pretty quickly, wouldn't y'all say? That's x squared. Now, let's go 2 to the x. And we plug in 0, we're at 1. We plug in 5, and we're at 32. All right, well, that's not too bad. X squared was 25. Let's plug in 20. And 20 is at 1 times 10 to the 6th. So that's 1,000,000. At 20, up here on x squared, we were at 400. Look how steep this is. So you're going to miss it real quick if I zoom out. So the red there is the quadratic. This purple one is the exponential. Do y'all see how much more quickly this one is rising? And if I go to 100, then we're at 1.2 times 10 to the 30th. That's a 1 followed by 30 zeros. This was a 1 followed by 5 zeros. Okay? So that's pretty crazy. Exponentials are nothing to ignore. So, let's analyze this real quick. Let's go ahead and put a series of dots on here. And let's do our little calculus game and do some local linearization there. Just draw little straight lines. All right, I won't make you guess and earn extra credit points ever again. How would you describe these those slopes there, Mitzi? Positive, negative, 0? Positive. I'd agree with that. This one looks like it's maybe about 1 or 2, right? I'll just make it 2. Now, if that's 2, Mitzi, what would this slope be? It kind of makes it actually, the way I drew it kind of makes it look a little bit steeper. It should be a little bit flatter. If this one's a little bit flatter than 2, like what would the slope be? So that's 2. This would be maybe, I'll give you an easy one. What about this one all the way down here? 0? Is that what you said? Yeah, this one, we're heading towards 0. We don't quite get to 0 in terms of the steepness, okay? Maybe about 0.1. Maybe about 0.5. That's about 1. Maybe this one might be about 1.5, okay? All right. Now, that being said, the slope here, what do you think, Robert, would be a reasonable approximation for that slope? Okay. Keep going. Maybe this one. Maybe 5, maybe 6, or something like that. It's definitely getting steeper. Can you all see that? All right. So if we take these slope values and graph them down here as the derivative, so a y value of 0.5 or 0.1 would be just a little bit above the x-axis. Y value of 0.5 would be a little bit higher than that. A y value of 1 would be about here. Y value of 2, 3, 5, 6. It's kind of interesting how, based on our approximations, what does this graph look like here, this derivative graph look like? Yeah, it looks like an exponential function. That's one of the really cool things about exponential functions, is that the derivative is also an exponential function. Now you might say, well, what exactly is that? And we'll figure that out here, hopefully this morning sometime. Yeah, but if not, that's okay too. Let's look at the logarithmic function. And this one grows oh so slow. We'll say log of x. Oh, let's just go home. Oh yeah, that's kind of what it looks like. I probably should have made this like look a little bit more flatter. It's basically this one reflected across the line y equals x, where this right here is the part that kind of kicks along the negative infinity x-axis, and this one right here corresponds to that exponential growth, only now it's sideways. So now it's ridiculously slow. So, at 5, we're at a value of 0.6. At 20, we're at a value of 1.3. So we've barely inched up. At 100, you're like, oh, surely by 100 we're going to be somewhere. Yeah, at 100 you're at 2. At 500, you're at 2.6. Like, oh my gosh. Surely by 1,000 we'll be at 3, right? You're exactly at 3. Because 10 to the third equals 1,000. All right, just think about that. While you're thinking about that, can you all agree with me that's really slow? Really slow growth. But let's play our local linearization game. That one didn't turn out so well. All right, so up here we're getting flatter and flatter, so closer and closer to a 0 slope, but not quite. I could put like that 0.1 there. In fact, I probably could utilize some of those same values. I could say this is 0.5, and I could say this is 1, and this is 1.5, because it's getting steeper. And then, 2, 3, 5, 6, or 8, or something like that. Because it's getting steeper, steeper. In fact, the closer you get to the y-axis, it gets steeper and steeper there. So if we're to take those slope values and plot them as y values, as up and down values, then we get something that looks kind of like this. We're thinking of the 5 and the 3 and the 2 and the 1.5 and the 1.5. 1 gets closer and closer to 0. So you get something that kind of looks like this. Didn't do the best job with that curve, but I'll see if I can get Desmos to do a better job for me. F of x equals log of x. G of x equals derivative with respect to x of f of x. There we go. So I can kind of see, I think they did a little better job than I did. You get a little bit of symmetry involved there. It's kind of neat. All right. It looks like we're going to have to talk about some special properties. Of logarithms. And here we go. The natural log of e is equal to 1. All right, you might be like, why is that? Well, here's the because column over here. Because what this means is e, that's this exponent right here, or sorry, that base, to some base, or sorry, to some exponent, equals e. All right? And so what number should go in that box? E to the whatever equals E, 1. Little bit of a reminder. Any base to the 0 power equals 1. So 5 to the 0 is 1. 10 to the 0 is 1. Anything to the 0 power is defined mathematically as 1. Now, let us convert that to a logarithmic expression or logarithmic equation here. So let's see how good y'all are, class. So log base, what's the base in this equation? B of 1 equals 0. So the log of any base of 1 is 0. So if we were to say, what's the log base 10 of 1? 0. What's the log base 2 of 1? 0. And, moreover, the log base e, so natural log of 1, is also equal to 0. Other properties. E to the ln x equals, oh, this is weird, x. All right, you're like, how in the world is that the case? Well, here's the because column, okay? So let's assume I have e to the ln x equals some question mark. So let's say we're not sure what it equals. All right? If I were to convert this equation into a logarithmic equation, I would say log base e of question mark equals the exponent, ln x. So, class, what's another way of writing log base e? Natural log. So, ln e of question mark equals ln x. What must question mark equal? Yeah, it must equal x. So question mark equals x. So therefore, e to the ln x equals x. If I haven't made it clear enough, I actually didn't say this, but e to the anything and natural log of anything are inverse operations, okay? Sort of like every addition has a subtraction enemy, every multiplication has a division, every square has a square root, right? Every sign has an inverse sign, every function has an inverse function. If you have f of x equals e to the x, then, sorry, not e to the negative x, e to the x, then the inverse function is the natural log, okay? So they're sort of like, not evil twins, they're sort of like superhero and, supervillain, constantly battling, and, reversing each other. So if you think about it like this, what if I had 5, okay, 5, and I did plus 2 minus 2? Where do I end up at? 5 again. But 5 times 3 divided by 3. Still back at 5, right? In the same way, if I have x, which is taken to the natural log, but then I take e to that power. It's sort of like I take x and do the natural log thing, then take e to that power. It's going to get you back to x. I don't know if that's helpful, but in the same way, this might make a little more sense. E to the x wrapped inside a natural log is equal to x. So take x, raise it, take e to that power, and then take the natural log. It's going to get you right back to where you started from. You might say, Mr. Goddard, where's all the calculus? We'll talk about the calculus probably next time. We're still doing some properties that we need to remember. Speaking of properties, here they are. Logarithmic properties. The logarithm of a times b can be expanded into log base a plus log base b. The logarithm of a divided by b can be written as log base a minus log base b. Do y'all remember, you speak truthfully now, you don't have to say it. Do y'all remember doing stuff like that last year in pre-cal, maybe? What about in Algebra 2? Did y'all touch on logarithms in Algebra 2? Normally you cover a little bit. What did you say, Kirsten? That's fine. I don't expect you to remember absolutely everything about all of your educational background. But you covered it a little bit. That's okay. Log of a to the b power. Robert, you remember what this one was? B log of a. It actually is kind of a little bit of a precursor to the power rule. At least it kind of looks like it, right? You just drop down the b, turn it into a coefficient there. That's kind of interesting. Okay. We are going to utilize those formulas a lot on Thursday, possibly Friday, depending if it runs into there, when we talk about logarithmic differentiation. But rather than me pausing every single lesson to go back and do a little bit of review, I figured we'd spend one day just kind of doing the quick hits, and then we'll spend the rest of this week doing calculus stuff. One more, or two more, I think, I guess maybe because of this. Those are properties of logarithms right there, this one right. This one is kind of weird. B to the x equals e to the natural log of b to the x. I think we kind of could infer that from, what did that kind of look like? Oh, compare that with this one right here. E to the natural log of anything is equal to the anything. So we have e to the natural log of anything is equal to the anything. All right? But we want to apply one of those properties here. So see, we've got the natural log right there. So b to the x equals e. That exponent right there is like this exponent right here. So we can pull that out front. So it's equal to e to the x times ln b. I'm going to kind of put a star next to that one. This is going to come into play, well, not tomorrow since you're taking notes, but Wednesday. So it's kind of weird. We'll use these facts on Friday. Thursday, Friday, we'll use this fact on Wednesday when we're actually taking the derivatives. Okay? So yeah, what we'll do tomorrow is we will come up with a formula for the derivative of exponential functions. First of e to the x and then of any base. So I'm super excited. It's one of my most favorite lessons just because the result is so amazing. All right? So I guess you'll get the spoiler tomorrow when you take your notes. All right? Sounds good. We're done a little bit early. How about that, huh?